All right, so of course this is a difficult problem since we're dealing with a many-body system with a large number of degrees of freedom. And I want to sort of draw three different perspectives to this problem. So in condensed matter physics, we we try to understand these many-body states, especially focusing on their, well, at least in some of the condensed matter physics, we focus on their universal properties, and such as a topological order captured by topological order, sometimes even a nice topological quantum field theory. Okay? There's also a more sort of quantum information theoretic perspectives on this problem, where we think about structures of quantum entanglement in these states, or in light of how they are used in fault-tolerant quantum computation. Okay. All right, so I'll try to exemplify these different perspectives to quantum many-body states using the example of topological Pauli codes, which is the subject of this talk, the title of the talk. They have one big advantage, one great thing about topological Pauli codes, that they're really simple. So we like simple things, simple models of topological states, and they are just really good codes because we can understand their error, error correcting properties easily thanks to the simplicity of the Pauli algebra. Okay, and even though I draw three of them, most of what I'm going to talk about will be about the universal properties, how to understand these codes from their universal properties, and also the what we can say about the structure of entanglement. Okay. So there will be some overlap to Michael's talk, but I hope I'll give you a slightly different perspective. All right. Okay, so now let me just define what I mean by a topological Pauli code. So let's first talk about Pauli stabilizer codes. Okay. So the ingredients are qubits, which just means we have n-dimensional space, Hilbert space, and the Pauli algebra on this space are generated by the shift x and the clock z operators. They satisfy the Pauli algebra, x to the n and z to the n's are 1, and they commute up to a phase, root of unity, nth root of unity. Okay, so this is one qubit, and of course we'll have a collection of qubits, and I'll only think about operators which can be written as products of single site x and z's. So I'll refer to these as Pauli operators. Of course, we can think about the sum of them, so it's really the whole Pauli algebra. And all the Pauli operators form a group under just operator multiplication, and that's a Pauli group, the curly P. Okay. So now I can define a stabilizer group. So a stabilizer group is a subgroup of this Pauli group, consists of commuting operators. So all the operators in the stabilizer group should commute with each other. And with the additional requirement that the only element in the stabilizer group proportional to identity is identity self. This is to make sure that you can set every stabilizer to 1 in the stabilizer group. So I refer to the elements of this group as a stabilizer. Okay. Now, once we define the stabilizer group, we can define the co-state, already the co-space, which are the space of states that are invariant under the stabilizers, all the stabilizers. I'll refer to it as the co-state. Okay, so this is the setup. Now, so far it's just Pauli stabilizer code without any notion of locality. So now I'll bring the locality into the game. So let's say the qubits are arranged in some sort of lattice, regular lattice. So for most of talk, for all the talk, it's two-dimensional. So, and this is the kind of typical arrangement. You see that the qubits live on the edges of a lattice, a square lattice, for example. It doesn't have to be square lattice, could be some other lattices. Let's just say that we have a square lattice. And now I'll put some additional requirements on this stabilizer group so that we can analyze it. They have some nice properties that we can analyze. So I'll demand that this stabilizer group is translation invariant, it's local, and it's topological. So let me explain what these three words mean. And please feel free to interrupt with any questions. So first, translation invariance. So if you have any element in the stabilizer group, G, then all the translate of G should also be in the stabilizer group. So that's translation invariance. Okay. And it's local, so the S should have a set of local generators. Local means that they have compact support, finite support on the lattice, local support. And this is technically, we should really do this on the infinite plane. On compact manifolds, you might have non-local generators, the logical operators. And topological here means that on the infinite plane, well, we can ask what are the operators that commute with the stabilizer group, and the requirement that the commutant of S is S itself. The centralized center of S is just S. Okay. So there's no other operators that can commute with S, but it's not in S. All right, so if the stabilizer group satisfies all of these requirements, the translation invariant, local, and topological, I'll call it a topological stabilizer code. Okay, so far, everything is defined just as a code, as a stabilizer group, which defines this code space, okay? But now I can, oops, yeah, this is right. So of course, no, we'll have to discuss the most basic and probably still the most useful topological code. That's a that's a toric code. So again, this is the standard arrangement of qubits on the edges of a square lattice. And the stabilizer group, here I just write the generators. No, we can generate all the elements of the stabilizer group by these two elements, by these two stabilizers, a product of X and X dagger around a vertex and a product of Z and Z daggers around a plaquette. Okay. And you can check that this satisfies all the requirements. It's translation invariant since we include this for every vertex and every plaquette. It's local. We explicitly have a set of local generators, and it's topological, something can check. Okay. So if you put this on a finite torus, n by n lattice, sorry, L by L lattice, for example, then you can get n square dimensional code space. The code space is n square dimensional. And all of these states, the code states, are locally indistinguishable, and they are really logical states. Okay. All right. So now I can turn this into a description of a Hamiltonian. No, it's completely equivalent, but sometimes useful to talk about it in this language. So if we choose a set of a translation invariant set of local generators, no, that should always exist by the assumptions that we have made, then we can write down the Pauli stabilizer Hamiltonian, basically just by summing up these generators, all the this set of generators, put the minus sign so the energy is minimized when S is 1. Okay? And we know these are just products of Pauli operators, so this is the Pauli stabilizer Hamiltonian. And all the terms commute. So this is exactly solvable Hamiltonian. We can find all the eigenstates, find all the energy eigenvalues. And these eigenstates will be labeled by eigenvalue omega of S, okay, for each of one of them, and plus the logical states, if you have any of them. And spectrum, so let's forget about the logical state for a moment. The spectrum is uniquely determined by the eigenvalues of Si, okay? And it's fully gapped in the thermodynamic limit. The gap doesn't depend on the system size at all. So it's really the simplest kind of many-body Hamiltonian that one can imagine. And the ground state has S equals 1. So the ground state is in the code space, and really the ground states are exactly the same as the code space. And excited states will have some of the S not equal to 1. Frank? Well, so if S is in the Pauli group, S dagger is also in the Pauli group. Things S dagger will be a power of S. Yeah, so it will be included in this sum, just by the structure of the Pauli group. Yeah.
You discussed the condition where the only operator proportional to the entity was itself.
Right. Because I want to be able to find a state where all the S is equal to 1. Otherwise, there's some frustration between these different terms, and you cannot minimize all of them. You cannot set all of them to 1 at the same time. So that's why I want to put this additional condition that the only element in the Pauli stabilizer group, the proportional to identity, is identity itself. Otherwise, you might find a situation where you have to put some of them to be -1 or some other phase. Okay, so excited states will have some of these s not equal to 1, and now sometimes they refer to as violations of stabilizers. Okay, so let's just do this, all of this thing for Tori code again. You can write it as a Hamiltonian just by summing over these generators. And the violations come in 2 types, right? You can have a violation of the vertex term that's drawn here as the blue dot, and you can have a violation of the plaquette term that's drawn here by the red dot. And these violations can be created and moved by string operators. Here is a product of z. The blue line is a z operator, and here is a product of x. Okay, you can use these operators to move the violations without creating more violations. Okay. And we can have this picture without lattice, where you just have a string that connects 2 excitations, and I'll refer to the blue one as E and the other one as M. It's a fairly standard notation. All right, so I've just defined a particular Hamiltonian with nice properties, but now I want to claim that this is really not just a particular state, it's a phase of matter, and just want to use this slide to define what I mean by a phase of matter. So when I say phase, it's really equivalence of different states, and this equivalence is defined in terms of finite depth circuit, more or less. Okay, so more precise definition is that if these 2 states are equivalent, if they can be connected by the quasi-local circuit, when the quasi-local here is really more or less up to some technical details, just a finite depth circuit, constant depth circuit. Okay. And we consider 2 states with the same, which are connected by a quasi-local circuit the same because they share the same sort of universal properties, which I'll discuss in a minute. Okay. So Tori code really represents a whole phase of matter, and it's a representative of that phase, which is particularly simple and easy to analyze. All right. Okay. So it's just one example of a Pauli stabilizer code, the Tori code. There are many, many other examples of 2D topological Pauli stabilizer code that people have come up with over the years. Color code, the XZZX code, etc. Okay. So we can ask whether these different codes, different looking codes, are related to each other in some way, whether they represent the same phase of matter. So they presumably have the same sort of computational power. And that's a meaningful question to ask. So how do we sort of classify these Pauli stabilizer code under this finite depth unitary equivalence? Okay. Here's one example. So there's a so-called color code. Okay, I haven't defined what color code is, but no. You can write it down as the code on the honeycomb lattice. It's actually equivalent to 2 copies of a Tori code. Okay. And it's actually equivalent up to a Clifford circuit, although it's not going to play an important role, whether it's Clifford or not.
Sorry, not your question. So the phi is the state, the code state, right? So basically,
yeah.
That you have 2 codes and you find 2 code states, and there was a finite time evolution between.
Right, okay. Right. So I guess I skipped this line. So this finite evolution can be generated by evolving with the local, quasi-local Hamiltonian for a finite time. I think Frank touched upon this in his talk too. Okay, so this kind of classification based on local equivalence, finite depth unitary equivalence, allows us to think about the properties that are sort of insensitive to microscopic details. Okay. All right, so in order to kind of discuss this equivalent, the phases, well, we like to have some invariants that tell apart different phases. Okay. So the invariants better something they can compute given the wave function. You can locally compute it, but it's a global invariant that can distinguish different phases. Okay. So Michael has talk about some of the invariants. And here, I'll try to define what we believe is really the full set of invariants for, at least for topological stabilizer codes, Pauli stabilizer codes. Okay. So the invariants are really given in terms of the anyons. Okay. So what are the anyons? Well, we have seen that these stabilizer codes have excitations, just violations of the stabilizers. Okay. So I'll refer to them as excitation or violations interchangeably. So the violations are local, they're just violation of the local stabilizers. And we can have this kind of super selection sectors of violations defined by this relation. So if you have local violations, but then we want to mod out all these violations which can be created locally, and then we get a finite set of equivalence classes, and these will be referred to as anyons. And we can create and move anyons by string operators, as we saw in the case of toric code. So equivalently, you can also describe these anyons as the string operators, which commute with all the stabilizers except at endpoint where excitations are created, and mod out the string operators that can be actually ended locally. Okay. And in the language of this sort of generalized symmetry, these string operators, they generate the one-form symmetry of the stabilizer state. Yeah.
Discuss the different phases, right?
Right.
Normally, we think of different UV theories that have locally more degrees of freedom, might have the same infrared phase.
Right.
We find this circuit as being a unitary circuit, and the two same number.
Yeah, that's a great point. I should have clarified this. I should have put this in the slide. So when we define this equivalence, we allow adding ancillars in trivial product state just to make up the Hilbert space dimension. Yes, that's an important part of the definition. Right. That should have been added. Yes, thanks. All right, so once we have identified these different anyons, or the string operators if you like, then we can talk about some physical operations on these anyons, which are invariant under the finite depth unitary. Okay. So first you can just fuse anyons, meaning that, or just multiply string operators that give you some sort of group structure on the set of anyons. So the anyons form a finite abelian group under this fusion. And the other invariant is that you can exchange two particles and you get a phase vector. Okay. So that's exchange statistic, and that's why they are called anyons. However, what's important is that you can actually compute this phase by very microscopically on the lattice once you know the string operators. And this is actually the method came up by Michael and Xiaogang some time ago. So without getting to all the details, so what you basically can follow this picture and compute some commutation relations of the operators and get the phase vector. And you can show that this phase vector is independent of where you are in this phase. Okay, it's invariant under finite depth local unitary. All right, so at this point, we have defined the abelian anyon theory out of a stabilizer state. Okay, so we have an abelian group of anyons. It's equipped with a quadratic form, so I just call this a quadratic form, that's a map from every anyon type to a phase vector, state of A, that gives you the exchange statistics. And that's really all the information you need. That specifies the entire anyon theory. Okay, you don't need anything else. But it's convenient to define this symmetric bilinear form, basically given by this equation. And it has an intuitive explanation, understanding as a mutual braiding between one anyon and another one. Or at the level of string operators, it's a commutation relation between two string operators. You can just having two string operators crossing at once, right? You can arrange them, for example, on a torus, so that they have one intersection, and just compute their exchange commutation relation, and that gives you this phase B. Okay. It's not independent information, but it's useful to have.
Why necessarily abelian?
The string operators are Pauli strings, and you multiply them, so it's abelian. And another way to think about this being abelian is that once you specify which stabilizers are violated and what's a violation, you fix the entire state. at least locally, up to global, like logical state. So that's also sort of characteristic of a billion ennion. Yeah, I said that. Yeah. For this definition, yes, we do. Well, that's a mean. So it's a string operator. Sorry, yeah, I should have said it more carefully. So it's a string operator along these non-contraptible cycles on a torus. Yeah, that's the only way to have two strings crossing exactly once on a torus. Does that answer your question? So it wraps around the torus, just to have one crossing. That's all I want. Ennion is an open string operator, and here, yeah. So this is a bit confusing. So maybe, yeah. So I've so far talked about ennions as endpoints of string operators. Of course, we don't have to have open strings. We can have closed string operators that just maybe use a different color, just wraps around the torus, and the entire reason that I need this is to get one crossing between two strings. That's all I want. Is that good? Yeah. Okay. All right. Of course, you don't really need this to calculate B. I mean, it's easy to identify what's the commutation relation. Okay, so for what is worse, there's this useful property of, well, this is kind of property of a B that anything that arises from topological state by the code or a ground state topological order, this B must be non-degenerate. Now, if you view B as a matrix, it has to be invertible. And this property is referred to as modularity, that the only ennion with B equal to 1 with every other ennion, then that's the only possibility is identity. That's the only one that with trivial braiding with everything else. Okay. All right. Any questions before I go further? But this is actually important for what I'm going to do. All right. Again, we can do this for toric code. No, we have already identified the generators of this group of ennions, the E and M, everything you can get by fusing them or taking powers and fuse them. So it's a Zn cross Zn group, and the fusion is just adding up these exponents mod n, just modular arithmetics. Okay? And the exchange statistic you can compute turns out to be this phase vector. Okay? So we have specified the entire abelian ennion theory for the toric code. Okay, so I claim that it's an invariant for a phase. So it's not terribly difficult to check this invariant, right? Okay, at least you can argue that because these properties are invariant under finite depth unitary, so it must be the same throughout the entire phase. Okay, probably the harder question, arguably the harder question, is whether that's all you need to know about the phase. Okay, well. So it turned out this question can be answered when you have topological Pauli stabilizer code or Hamiltonian translating invariant, translating invariant, and all the qubits are prime dimensional. Okay? If that's the case, then there's a beautiful theorem proved in this series of papers. First for the p equals 2 case for Z2 for qubits, and then generalized and refined. No, loopholes are filled in this paper by Zhou Wang in 2018 that shows that if you have such a topological Pauli stabilizer code with prime dimensional qubits, then up to a constant depth Clifford circuit, it's just equivalent to some copies of toric code, ZP toric code. Okay, so that's a complete invariant. Once you know this number, the invariant is just now a number. It's a number of how many number of toric code you have, and then you know this thing up to finite depth, actually Clifford circuit. Okay, so this is a beautiful theorem that really answers the question in full generality for prime dimensional qubits. Okay. All right, but the question still remains if you have other dimensions, like composite dimension or powers of prime. And that's still open, but we can ask whether there's anything that's actually different from copies of toric code when it comes to non-prime dimensional qubits. Okay. So here I'll give example that was first described in this work. So again, you see this lattice, the same sort of lattice, but we have 4-dimensional qubits. Okay, so instead of prime dimensional, it's a 4-dimensional. And here's the stabilizer group. So the details are not terribly important. Just know this, you can check this is a local translation invariant set of topological stabilizer group. Okay. We get 4-dimensional code space. Again, we can calculate this and get 4, and they are all logical states. Okay. All right, so what's the anyon theory? Well, the anyon theory turns out to be what's called a double semyon. So these are the string operators. One of them is just the product of z squared. You can check that z squared commutes with everything, because z squared commutes with x squared, and it commutes with the way that x are arranged here. Okay. So z squared is a string operator. The product of z squared is a string operator. And the other string operator is a little more complicated. It's the product of z and then has these legs of x. Okay, remember, x and z are now z4 Pauli operators, not z2. Okay. All right. And this one's called B and this one's called S. So following the definitions, you can calculate all the fusion rules and statistics, and we'll get these results. So all of them are like Z2, they fuse to 1 if you just square them. And S now has statistics I instead of just okay, it has I statistics, and then B is a boson, and if you fuse them, you get minus I. Okay, this is not toric code. Okay, toric code has plus minus 1s for all anyons, but it's still Z2, so it's a different kind of anyon theory. So it's a different phase for sure. So, so where does this come from? So that's an anyon theory, and we know this is really in a different phase than toric code. Okay, so where does this come from? Well, there's actually the idea that behind this construction that's from thinking about the universal properties. Okay, it might not easy to just come up with a construction out of blue, but it's really motivated by this idea of getting this double semyon anyon theory from a Z4 toric code. And you can kind of see that it's really sort of embedded in the Z4 toric code. The fact that you start from qubits with four states. Okay, so the idea that if we start from Z4 toric code, but then we condense this particular excitation. This is actually a boson they can check. So you just drive a boson condensation of the E square M square anyon. And what it means, sure.
Does the set of all the anyon operators generate the full qubit space? Do you require that? Or?
Also, I don't require that. It is true for the stabilizer code. All the short string operators of anyons, they generate. Yeah, right. You get all the states by acting with short string operators. Yes?
Does this condensation correspond to adding a concrete local term to the Hamiltonian?
Yes, that's a term that I need to add. Right. Yeah, right. That's these are the terms basically. But just to give a picture of condensation, what we do is that what needed to be done is that you create all possible configurations of these E square M square anyons and superpose all of them with equal weight, and that's the new state. Okay, and this can be done by, although I use the word measuring, it's really adding. So for the Hamiltonian, you basically add these terms to the Hamiltonian, and these terms actually are the short string operators, shortest string operators that create a pair of E square M square anyon. So just by adding these two, did I have a Hamiltonian? No, too bad. Okay, so I didn't have a Hamiltonian with Z4 toric code, but you can imagine starting from a Z4 toric code, and let me get back to this line. So it's actually, like we can see it from here. So imagine you had a Z4 Hamiltonian to start with, and then we add these two terms. And then we assume that these two terms are really huge, with huge coefficient, and the only thing that left under the presence of these two terms are stabilizers that commute with these two terms. And turns out that these are the only ones that commute with the two additional terms that I added to the Hamiltonian. Okay, so that's how you get this new Hamiltonian. Or you can think about it in the stabilizer group. So you just look for everything that commute with these two additional terms. Yeah?
Terms you're adding short open string operators?
Yes, they are short open string operators, sorry, yeah, for this particular enyon. All right, so we can even analyze the effect of these terms without actually looking at the Hamiltonian. We can analyze at the level of enyon theory. There's a well-developed mathematical formalism to analyze what happens if you do this kind of enyon condensation just at the level of enyon theory or TKFT. So, let me just go through this quickly. So you basically want to identify E square and M square enyon, which were non-trivial enyons in the Topological code as vacuum, as part of vacuum, since we create superposition of these enyons. So that means many enyons are now identified. EM is the same as E cube M cube because they differ by E square M squared. They also confine many other enyons. If those enyons, the string operators do not commute with E square M squared, then they become confined. They are thrown out from the Hilbert space, low energy Hilbert space. Okay, for example, E is confined because it has -1 braiding with E square M squared. So the only ones that are left, which I call the confined, are E square. This is identified with B. That's why you see the Z square. EM, so this is the blue string with lots of legs. That's EM, the S, and then you get B times S. So all of this can be done even before writing down Hamiltonian, and then you can try to implement the Hamiltonian and get this new stabilizer code. Okay, so this is just one example to show that you can get something different from just copies of Tori code. It's not that boring if we allow composite dimensional qubits. Okay, so now comes the question. So we can now ask a question a little more sharply. What exactly are the enyon theories they can possibly get from topological stabilizer code? Okay, so to state the conjecture, I mean, we don't have a theorem. We can state what I believe is true. I need to introduce a few other properties of enyon theory. Okay, so once we're given this enyon group and also the exchange statistics phase, we can compute what's called the Gauss sum, basically. So in this case, it's literally Gauss sum because it's quadratic form. On a finite group, you compute the Gauss sum, you get a phase vector. Turns out you get a phase vector, which is e to 2 pi I over 8 times the number c minus. This number is an integer in this case, and it's called the chiral central charge. For the experts, no, this is chiral central charge of the chiral component field theory on the boundary of the state. Okay. So without really any explanation, we just claim that if the C minus is not 0, then if you have an edge of the system, must be gapless. It must be gapless degree of freedom propagating on the edge. Okay. Now, so this is obstruction to having a fully gapped or topological boundary for this enyon theory. Okay. And it's entirely determined by mod 8, because it only enters exponent mod 8 by the statistics. Okay, so if this number turns out to be 0, then the edge may still not be gappable. Okay, and the full condition of gappability is a little more than just having no chiral central charge. It turns out, from these works that we learned that the correct condition is that A has to have what's called a Lagrangian subgroup. Okay. A Lagrangian subgroup in this context is just a certain number of bosons which braid trivially with each other. Okay. And the number has to be exactly the square root of the number of enyons. So if the number of enyons is not square, there's no Lagrangian subgroup. If it is square, then there has to be this number of bosons in order to have a fully gapped boundary. Yes?
Condensing enyons from Z4 Tori code. But is it clear from this that it cannot be
Yeah, because the statistics are so it's you can check that the statistics cannot be reproduced by the copies of Zn Tori code. Right, this is something you can sit down and check. Okay.
That provides an example that if you don't have a lower point dimension, you cannot
So that's not exactly what I was saying. So of course you can still get Tori code when if you have Zn qubits, you can still get Zn Tori code, but now you can get other things. So I'm going to state the precise conjecture. Okay, so with these, we can now sort of have a hierarchy of anyon series measured from how far away they are from a stabilizer state or commuting projector Hamiltonian. Okay, so on the top we have this anyon series that has C not equal to 0 mod 8, and they have chiral edge states. For example, you see many of these in fractal quantum Hall states. The first one that I discovered experimentally. Okay, then there's the next level down where C is 0, so there's no obstruction from C, but there's no Lagrangian subgroup. Okay, so these are non-chiral, you can say, because there's no chiral central charge, but then they still have protected gapless edge states. Okay. So these are also discovered experimentally with 2/3 quantum Hall states, and this particular Chern-Simons theory, the anyon theory correspond to this Chern-Simons theory, has this property. Okay. Now we can also, then we can go to these series with a Lagrangian subgroup, which allow fully gapped boundary. And all of these can be realized with Pauli stabilizer codes using the trick that we discussed earlier, by first kind of embedding into a larger copies of number of Tori codes, and then do some condensation to write down a Pauli stabilizer code. All right, so now we can sort of state the conjecture. So these are the known facts. So if you have prime dimensional qubits, and they are classified by the anyon theory, which is always a stack of Tori code, and that's a theorem. And then we also have constructions, explicit constructions in terms of Pauli stabilizer codes for all the anyon series that have gap boundary. Okay, we have all of these can be constructed at least with Pauli stabilizer code. Okay, so the conjecture is that the only thing that you can possibly realize by the Pauli stabilizer codes are exactly the anyon series with gap boundary. Okay, in particular, you cannot realize anyon series either with C equals not equal 0 or just without the Lagrangian subgroup. So I just want to note that there was a very recent paper this Monday from this group that claims a proof for the C not equal to 0 case, even for more general types of states. Okay. All right. Okay, so let me see how I'm doing in time. Yeah. I mean, why they can be realized at Pauli stabilizer codes. So it turns out that this construction, by first going to a larger abelian group, going to some number of Tori code and then do condensation, can realize all these abelian twisted quantum doubles. So there are explicit constructions for all of them. Whether that's all that can possibly be realized, that's a question. And whether that's the only invariant for composite dimensional qubits, that's unknown. All right. Okay, so at least we have some sort of a plausible conjecture for what phases you can possibly get in Pauli stabilizer code. No, there are many, but not all. Okay. So again, yeah. For all the known constructions, you can find explicit boundary conditions, and it's just gapped, right? And then usually the term that you need to add are let me just make a couple comments here. So there's this Lagrangian subgroup, which are a set of bosons, and they have mutual commuting, mutual braiding, completely trivial. So what you need to add is to basically add a short string of these bosons to the boundary. And they commute and they can gap out everything in principle. All right. Okay, so let me now sort of briefly discuss what you can do beyond just simple Pauli stabilizer codes. Okay. Well, one direction can go is to just forget about finite dimensional Hilbert space and let's think about continuous variables, which are actually also important for many experiments, especially those carried out at Yale. People only care about oscillators there. So whether we can, well, so I'm not going to define this term precisely, but you can imagine, but let me just sort of first define the kind of hierarchy of variables. So of course, quantum mechanics usually starts from continuous variables x and p, Heisenberg, the standard commutation relation. Okay, and we can kind of make it compact by starting from say p squared over 2m, just a free particle, and add a periodic potential. Then in the limit of u much larger than 1, then you kind of go to the low energy space at the bottom of this potential, which are x equals integers. So you have the discrete set of states, infinite discrete set of states, and that's really equivalent to a rotor degree of freedom. We compactify the x on a circle. We can do a little more by adding another term, cosine some integer times p, okay, on top of the cosine 2 pi x. And now we further identify x with x plus n, and we have a finite number of states. And this is the GKP code, the single mode GKP code. So in this language, at low energy, we have n-fold quasi-degenerate states, and the logical operators on this now a qubit is just e to the ip and e to 2 pi over nx. You can check that they commute with everything. The commute with these two cosine terms. So what I'm going to do is to generalize this to multiple numbers of a lattice of these continuous variables, the oscillators, by thinking about Hamiltonian of this form. Okay. So this part is not, the quadratic part is not important. For what I'm not that important. So we're going to focus on these cosine constraints, okay, because that's what makes everything sort of discrete. All right. So similarly, just generalizing the Pauli stabilizers, we can have topological continuous variable stabilizer codes, which are defined as roughly as follows. So we have a collection of these oscillators or continuous variables forming some regular lattice. Okay? And on these oscillators, we have displacement operators, which are exponentials of just some linear combinations of x and p. Okay? And while I'm still going to use the same name, stabilizer group is a set of commuting displacement operators. That's what I'm going to call a stabilizer group in this case. Okay. I think this is also known as a multi-mode GKP code, but with a locality requirement, of course. That's what we want to do. Okay, so we can also assume that this stabilizer group is translation invariant. Local has a set of local generators, and topological just basically the same meaning. Okay? And we can define a code space by the same definition, essentially, that every stabilizer, every displacement operator in the stabilizer group is 1. Okay? And I'm going to put additional requirement because, yes. Can you say again?
What's the choice in when you choose all the possible in your stabilizer group?
Oh, why do I have all of these?
No, like what's the value of the
Oh, this is just unspecified at the moment. Just writing down some linear combination. Yeah, of course. U and V will have to have, we have to give the values for these numbers. I'll show that next slide. Okay, so I need to make an additional assumption that on the finite dimensional, in the finite system, the code space is finite dimensional. You might end up in the situation where it's infinite dimensional or it's even just a continuous variable. We are not interested in that situation because it's being shown that that cannot be, that encoding of a continuous variable into a collection of continuous variables is not fault tolerant. Okay. All right. Okay, so here's an example. The details are complicated, and I'm not inviting you to looking into details. But the point is that we have a set of, this defines a set of stabilizers. Okay, each of them is just a displacement operator. They are complicated. They all involve 1, 2, 3, 6, 7 operators, but they're all local. And you can check that they all commute, okay, and topological. Okay, so what do we get out of this? Well, the claim that this code realizes in an appropriate sense, yeah.
How do they read this irrational exponent?
Yeah, just put the irrational. So really mean that z, for example, z square root 2 is e to the I square root of 2 times x.
How all the exponents are compatible with the periodicity of x and t?
There's no periodicity because x is just a continuous variable. It's an oscillator. It's not compact. Right. So all of these will kind of compactify this collection of continuous variables. But each one of them, to begin with, is just a continuous variable, non-compact continuous variable. All right. Okay, so I want to say that this code that I wrote earlier realizes this Anyang theory in the appropriate sense. Okay. So first, this Anyang theory is one of those that is non-chiral, so has c equals 0 because of the opposite signs on the 2 levels, but it doesn't have a Lagrangian subgroup, so it has to have gapless edge states, by the sort of general argument, field theory-like argument. Yeah.
Is a continuous variable equivalent to the previous 2-1 take the n like it very large?
I'm not sure that's really the right way to think about continuous variables. I think we should just think about continuous variables on their own.
You say chiral is a statement that c is not equal to 0 mod A.
That's the working definition. That's a working definition.
Is this really an extent to be parity invariant?
It's not parity invariant.
So it is chiral.
In that sense, right. Yeah, it is not parity invariant, it's not time reversal invariant, but by chiral I just mean c not equal to 0 mod 8. I know, right, yeah. Okay, so this theory is one of those that doesn't admit Lagrange subgroup even though it has c equals 0. So you can count the dimension of the code space, it's 8. So already kind of suggests that no, it's not a square of the integer. And to kind of really to check this claim, so first thing you can do is to find all the string operators, the logical operators that commute with the stabilizers. And that one can still do. And the short string operators are written here. Again, they're complicated, not particularly pleasant to look at, but you can write down them, and we can compute these statistics, and turns out to agree exactly with this Anyang theory. Okay, the fusion statistics agree with the Anyang theory. Okay, so at least at this level, we realize this Anyang theory as a kind of an invariant for this topological continuous variable stabilizer code. Now, just want to make a remark that this construction turns out to be very closely related to this discretized consignment theory on lattice by Eliezer and Semenov back in the 90s. There's a long series of effort to discretize consignment theory, and this I can comment on the relation offline if you're interested. Now, one caveat with this kind of Hamiltonian, with kind of this code, is that if you naively turn into Hamiltonian version just by summing up the local generators of stabilizer group, because the variables are continuous, you get a gapless Hamiltonian. Okay, but that can be fixed by adding back these quadratic terms, which opens a gap, and we can check that everything stays the same. Okay, so this is example where you can go beyond the Pauli stabilizers, but now we have to use this continuous variables. Yes? Yes, yeah, that, in this case, we can analyze it. I mean, that requires some work. It's not supposed to be very immediate. It's not immediate.
It seems like here you had a pack, one form specifically linked to the annual.
Right.
Which comes from non-pack, local degrees of freedom. Get that?
Yeah, so because we have these constraints, the integer constraints, these constraints are essentially compactifying these continuous variables, but in some complicated way. Okay. So you can write down these string operators. Yes, I think I know where the question comes from. So naively, it looks like these operators are non-compact. You raise it to any power, it just keeps going. However, you see that, for example, if you take this one, W2 is a product of just a series of these operators multiplied together along a path. If you square it, you'll find that it's actually equal to one of these stabilizers. So it squares into a stabilizer. That's what I mean. That's compactification. Okay. So acting on the code space, it's order 2. So in that sense, it's order 2 anyhow. It's not irrational. It's like I and e to the I pi minus I pi over 4, whatever you expect from this theory. Right. Yeah. It's no longer commuting, right? So you can still analyze a problem perturbatively. So because we are, yeah. So I didn't say that. So we add these terms as like weak perturbations to the cosine terms. So you can still do perturbation theory. You open up a paper by Michael and Sriram, just know that this type of Hamiltonian is analyzed very thoroughly and just follow the prescription.
But in your ground state, still stable, the code space.
You mean the stability of the code space?
Yeah.
So that I do not know the answer because all the stability theorems that we know about topological order states, as far as I know, they are proven for finite dimensional Hilbert space to begin with, using LibreOptimists and bounds. And to my knowledge, that hasn't been sorted out for continuous variable Hamiltonians. It's a tricky question. Okay, so mathematically rigorous statements do not exist for continuous variables, although we believe the gap still enough to protect the ground space, the code space. Yeah, Michael. Yeah, there's some reasoning. It's not out of nowhere. But the reason is kind of a very wide one. So the idea that you start from X and P, collection of X and P. So everything I'm saying now is just very vague and extremely just some way to guide the thinking. So we start from X and Z, X and P. I want to think about it as an R gauge theory. It's non-compact R gauge theory. But then I want to compactify it to U1. So we know to compactify R to U1, well, you can add, you can gauge a one-form symmetry. That's probably the best way to put it. You gauge a one-form symmetry, a Z one-form symmetry, compactify R to U1. Okay. But it turns out that once you do that, naively you do that, you can choose a one-form symmetry that's actually give you this first vector. Okay. And then, but that's not enough to gap out everything. That's not enough to fix all the continuous variables. It turns out you have to add another set here. And then you get this. That's how we arrived at this set of generators. Now the tricky part is that to gauge a one-form symmetry, what actually happens is adding the short string operators. I mean, I'm using the word. I'm abusing that word, short string operators. And you want to make sure that they commute. And somehow I have to do this weird thing, okay, to make sure that this short strings commute. And this we don't have any understanding. It's just some microscopic short distance detail that turned out to work. But it has this connection with a discretization scheme that's written down 30 years ago in this paper. Turns out to have exactly the same sort of short distance detail. And also related to, okay, I can comment on that later. Right. Yes? Okay, so this is back to like this relation between gauging one-form symmetry and condensation, right? So for anyon series, at level of TKFT, they are the same. That's all I'm saying. So what actually we did to sort of derive the Hamiltonian is adding short string operators. But gauging one form is like a useful way to think about it abstractly. All right. Okay, so I just want to point out that, to say that, no, there another way to going beyond Pauli is that you just, let's not stay with abelian groups and go wildly into this kind of category, the world of categories. And there are generalizations of stabilizer code, and well, haven't talked about this yet, for like fusion categories that realizes non-abelian anyons, etc. Okay. All right. So I think I'll pause and see whether there are more questions for this part. If not, well, let's continue. Okay, so I want to now say a little bit about the structure of entanglement. No, some simple facts. But before that, let me first generalize the stabilizer, Pauli stabilizer code a little bit more. So I want to discuss, it turns out that's probably a better setting to discuss entanglement, the subsystem code, okay? And let me start with example. See how much time I have. Okay. So now we go to a honeycomb lattice. Okay, so this is a honeycomb lattice. The edges are labeled as X, Y, and Z, just the 3 different orientations of the edge. Okay. And each side, instead of edges, has a qubit. It's just a qubit. So we have these Pauli matrices X squared, X, Y, and Z. The Pauli's X and Y and Z. Okay. So define a stabilizer group generated by this product. So it's X, Y, Z, X, Y, Z. Okay. You probably recognize this is really the Kitaev's honeycomb model. Now, if you take this as a stabilizer group, it's translation invariant. It's manifestly local because we have a set of local generators. However, it's not topological according to a definition I gave earlier, because there are operators which commute with this stabilizer, but it's not a stabilizer. Okay, so these are the product of X, Pauli X along X, the product of Pauli Y along Y, and etc. And it turns out that if you look for the center, the commutant of this stabilizer group in the Pauli group, it is exactly generated by these short string operators, if you like. Okay. So it's not topological in that definition that I gave earlier, but it's still kind of a nice stabilizer group because the commutant is locally generated. Okay, so this example of a subsystem code, it's in the sense that the stabilizers are not really sufficient to completely specify the state. There are still other states represented by which are representations of this algebra. Okay. All right, so that's example of Pauli subsystem code, and here's the formal definition. Okay, so again we start from a stabilizer group, which is translation invariant and locally generated. But then there's also a gauge group. So this is not to be confused with the gauge group in the gauge theory, right, in standard models. So just the name in the error correcting code literature, this is called a gauge group, G. The G is essentially, in this context, the commutant of the stabilizer group. And we require that this G is translation invariant and has a set of local generators. In general, it's not true, but we require this on the infinite plane at least. Okay. And that's the new definition of topological for subsystem code, is that both S has a set of local generators, and the center of S in the Pauli group is proportional to this gauge group, which is also locally generated. Okay, but the point is just that the stabilizer group is not large enough to really kind of fix the code state. Okay, so we can still define a code space, just as the space of states invariant under all the stabilizers, and we can split Hilbert space into a direct sum of the code space and with its complement. But now there's further structure in the code space. Okay, so we can always write the code space as a tensor product of, well, the gauge space and the logical space. And the gauge space is representation of this gauge operators, which are the operators in this gauge group, if you quotient out the stabilizers. And this space is now extensive instead of just a constant in the case of stabilizer group. So that's the only difference. So it's really a subsystem of some stabilizer group, if you like, or some stabilizer code. All right. Okay, so let me just comment why this is interesting to think about. because oftentimes you see that the gauge operators are very simple. In the previous example, the gauge operators are two-body, just 2x on each edge. Although that example is bad in that sense because it actually doesn't give you any logical state. But you can come up with examples where there's non-trivial logical state and the gauge operators are simple. Maybe Michael and then. Sorry. The gauge operators are everything that commute with the stabilizers.
But how is H gauge?
Sorry, H gauge. How? Yeah, so maybe it's easiest to, for example, do it on a sphere, let's say. Then this entire code space is gauge space. Now, if you're on a torus, then there might be logical operators. So logical operators are usually easily identified as from like these topological string operators, and the rest are the gauge space. So the gauge space is a space where this algebra of the gauge operators act irreducibly and faithfully once you mod out the stabilizers. So that could be used as a definition of the gauge space. All right. What's it? Yes. The gauge operators don't have to commute. The stabilizers do have to commute. Yeah. Okay. So just like the Pauli stabilizer code, we can also associate to every topological subsystem code abelian theory. Okay. But because now we have generalized the notion of a stabilizer code, now the abelian, essentially all the restrictions of the abelian series are lifted. Okay? Remember that in the case of topological Pauli stabilizer code, abelian series has to be modular, has to have a Lagrangian subgroup, at least that's a belief. But right now there's no restrictions, no limitation whatsoever. As far as we know, everything can be realized. Every abelian theory can show up for some subsystem code. Okay, so there's no required modularity. There's no required to have a Lagrangian subgroup.
What do you mean by non-modular?
Oh, just this is the B, the matrix B. Now the modularity means the matrix B, the braiding matrix, has to be invertible. But now it doesn't have to be. The determinant could be 0. The definition of the anyons now are more or less the same as before. I mean, I just copied these definitions without any change. You can still talk about local excitations, but now there's no Hamiltonian, so it's really excitation just being violation of stabilizers, and mod out by the ones that can create it locally. And you can also define in terms of string operators. Again, these are the one-form symmetries of this code states. Okay. All right, so for this example that I discussed earlier, you can just follow definitions and compute. Yep.
So when you say this is a one-form symmetry, is it the one-form symmetry only in the code space or in the full Hilbert?
So in the code space, the one-form symmetry are like the honest topological one-form symmetry. Okay. In the full Hilbert space, it's not a one-form symmetry anymore. Well, so these are just operators, right? So I guess it doesn't really make sense to ask whether it's a symmetry. There's no Hamiltonian so far yet. So I'm saying that the code space is defined by the stabilizers being 1. So almost by definition, these one-form symmetries, these operators are one-form symmetries in the code space. Okay. So
they could fail in the full Hilbert.
They could fail in the whole full Hilbert space, right? If you have a Hamiltonian, they don't have to be the full one-form symmetry. It depends on the choice of a Hamiltonian. For example, if you take the Hamiltonian to be sum of the gauge operators, then they are one-form symmetries of the Hamiltonian, because the gauge operators commute with the stabilizers. Okay, so if you take this example and then just follow definition to compute, you'll find that there's just one type of string operator, non-trivial string operator, and it's a fermion. The anyon they create by cutting the string operators open is a fermion. Okay, so the entire anyon series is very simple, just identity and fermion. And it's not modular because we know fermion, if you braid a fermion around a fermion, you get nothing. You get 1. So it's kind of transparent to everything. Okay? So that's why this is not particularly useful as a code, because it actually doesn't give you any logical states. But it's an interesting example showing that you can get these kind of non-modular series from subsystem code. All right, so these are sort of the natural generalizations where, and I think I didn't finish the comment on why it's sometimes a good thing to think about, because the gauge operators are simple. In some examples, like here, these are two-body. So the measuring these gauge operators give you additional information about the code states, right? You can figure out actually stabilizers by a sequence of measurement of the gauge operators. And it's good to have simple gauge operators to measure. Yes?
I'm afraid I missed a basic point. Since you have stabilizers, why can't you have a Hamiltonian over the stabilizer?
We can write Hamiltonian stabilizers, but that will not fix, that will have extensive degenerate ground state. We can do that. That's no problem. Sorry?
Roughly, there are not enough of them.
There are not enough stabilizers to fix a state. That's why it's a subsystem code. All right. So I will, yeah. So if you have a number of qubits or whatever, qubits to be n, you have some number of independent stabilizers. Then the number of states is roughly, so let's say 2 to the n minus n of qubits minus n of independent stabilizers, roughly up to order 1 factors.
So in this particular case, you just take all the stabilizers.
Right.
What's the answer? It's scale. Is it exponential in the total number of states?
Yes, it is exponential in the total number of states. Right.
But if you add the gauge generators into the stabilizer Hamiltonian,
it depends, but I'll come back to this. Yeah. So.
Pick a set of commuting gauge constants.
Yeah.
And add it to the Hamiltonian.
You
get a nice topological state.
So by doing that, you can recover these topological stabilizer codes, for example. Right. But just if you want to add commuting terms back to the Hamiltonian, then you just get back these earlier stuff. You kind of complete the. Now there's modularity. Okay, so maybe actually since there are these questions, let me jump a few slides ahead. I'll come back. So okay, that's this is what was asked. So we can now create a more interesting Hamiltonian by, for example, adding gauge operators to the Hamiltonian. Now the gauge operator does not commute. That's fine. We just have a non-commuting. We have non-commuting terms in the Hamiltonian. We don't know exactly. Generally, it's not exactly solvable, but at least we know there's exact one-form symmetry on the lattice model. Okay? And this example was extracted from this famous Kitaev's honeycomb lattice model. It's hard to probably look at the details, but after some relabeling of x, y, and z, it's exactly the one that I talk about. I'm Hamiltonian just adding all the gauge generators. Okay? And in this case, turns out this Hamiltonian is exactly solvable, and that's related to the fact that the one-form symmetries are fermions, so you can kind of fermionize everything and solve this model and even get a phase diagram, a complete phase diagram, where we know what every one of these things is. The shaded areas are all toric code. The one in the middle is gapless, and in the right middle, the isotropic point is actually a Majorana, gauged Majorana CFT. Okay. All right, and you can study other Hamiltonians playing with, for example, the Z3 Kitaevs. But let me skip this and back to the point I want to make about long-range entanglement. So in this subsystem code, if you impose these conditions, the stabilizers, we get a huge Hilbert space of states, which are not ground state of anything. Well, they are ground state of Hamiltonian as a sum of stabilizers, but they could be very complicated. But we can still make some statement about the long-range entanglement in these states. Okay. So first, let me define kind of a very rough pattern of classification of long-range entanglement. So what's a short-range entanglement? Okay. Well, for the working definition here is that short-range entangled state is whatever that's connected to a product state by a finite depth local circuit. So that's short-range entanglement that can be created by just doing local evolutions. And long-range entanglement states is whatever that's not short-range entangled. Okay. Not pretty useful definition, but no, that's one definition. Okay, so now let me just state two theorems. The proofs are actually not difficult, but I'll just state, and I'm happy to explain it. So if for this subsystem code, if any of the theta is not 1, okay, for at least one A in this anion group, then all the states in the code space are long-range entangled, meaning that they are not connected to a short-range entangled. They're not connected to a product state by a finite depth circuit. Okay, so we know all of them, whatever they are, they must be long-range entangled. Okay, we can refine it a little bit further to a statement about separability of the many-body states. Okay, so this is the next theorem. If you find a pair of anions which may or may not be the same in A with a non-trivial braiding, okay, then all the code states are long-range entanglement that we know, but they are also not bipartite separable. So here's what it means. So if you have a bipartition of the system into A and B, connected parts, then bipartite separable means that you can write the state as up to a finite depth circuit, a tensor product of a state on A and tensor product state on B. That's bipartite separability. And a statement that if you find such a pair with a non-trivial braiding, they are not bipartite separable. Okay. Okay, so there's some constraint on the structure of the state, just from the fact that we know there's these anions, these one-form symmetries, if you like. All right, so now I want to kind of leverage this, generate this a little bit further, as I'm running short on time, that these kind of symmetry operators, which forbid, just doesn't allow symmetric short-range entangled states, they're said to be, well, at least here again, for this talk, for the working definition, they are said to be anomalous. Anomalous symmetries are whatever that forbid short-range entangled states. Okay, and the general pattern that that we see that is anomalous symmetries in different dimensions. They give you different sort of constraints. Of course, they usually lead to long-range entanglement because by definition they forbid short-range symmetric short-range entangled state, but they also lead to some constraints on multi-part separability. Okay, so here's another example that I really like. So if we go to one dimension, just a spin chain, just simple spin chain with periodic boundary condition to be clear. And in that case, it's a zero-form symmetry, just a global symmetry acting on all the spins. And if it's anomalous, then we can show that the state is not tripartite separable, although you can come up with bipartite separable states. Okay, so it's weaker than the one-form symmetries that we just saw on the earlier slide, but it enforces a tripartite inseparability. Okay, so explicit example of this kind of anomalous zero-form symmetry is this Z2 symmetry written down first by Michael and Meng Cheng in a paper 10 years ago, 12 years ago. It's a Z2 symmetry, the product of X on each, so it's a chain of qubits, X on each side, and control Z on each pair of neighboring sites. And here, not tripartite separable means that if you have a state invariant under this operator, you cannot write it as up to a finite depth circuit as a product of tensor product of states on A, B, and C. And I want to emphasize that it has to be respect to this particular tripartition. You can come up with other tripartition where it is possible to write it as product of A, B, and C. So the statement that there's for these if it's bipartite separable, now the question is on the one partition, on one part, can you actually cut it further? Okay. It turns out that if you want to write down states which are bipartite separable, then these are long-range correlated states on each part. And you cannot cut it further. So that's actually a sense of the proof of this, is that you show that if you first cut into 2, it's long-range correlated, so you cannot cut it further. Okay, and yeah. For every tripartition of this form, of this topology, A, B, and C adjacent to each other. Yeah. You can come up with tripartition where, for example, you make another B over here. Right. You can have disconnected parts. But that's the one that we don't have a theorem. The theorem holds for this kind of tripartition. Okay. And then there are generalization of this statement to higher dimensions, which are not as strong as the one that we can prove in 1D for some technical reasons. But the conjecture that states invariant under zero form symmetry is a group cohomology anomaly. I'm not going to explain this. It will take me too long. But in, for example, D-dimensional spatial dimensional spin system are not D+2 partite separable for particular partition. Okay. So there's a kind of a sequence of constraints on multipartite separability of states. All right. So a kind of useful, a fun consequence of this theorem is that you can come up with mixed state in 1 dimension, which are 2 separable, bipartite separable, but not tripartite separable. Okay. And it's very easy to write down the state. You take this operator and just write down the maximum mixed state in the subspace where W is 1. That's all you need to do. So it's proportional to 1 plus W. That's a projector into that subspace. And you normalize it to be a density matrix. Okay, so one can show that just using the thing that told you on the earlier slide, that rho is actually 2 separable with respect to any bipartition, but it's not 3 separable for this kind of bipartition, tripartition. Okay, so it's a kind of a weird state that goes against the intuition that we have about pure state, right? Pure state, if you have 2 separable state with respect to any bipartition, it's 3 separable for this kind of tripartition. But for mixed state, you can have this kind of weird state sitting in between 2 separability and 3 separability. Okay. All right, guess I've talked about these. So I'm running short on time, but yeah, I'm gonna excuse myself because the computer is not it was giving me a hard time, so I'm gonna buy myself a little bit more time. That was not by purpose. All right, so for the last 5 or 6 minutes, I'm gonna switch gears a little bit to talk about some questions that are inspired by the error correction, quantum error correction. Okay, so let me just now get back to the familiar Z2 toric code or surface code, and we know they're error correcting codes. So let me just review what that means. Okay, so just take a very concrete example. Let's say that the Z2 toric code is now living in a noisy environment. It's subject to some noise. And just to be clear, let's say we have some noise, X, noise operator X, which occurs with probability P. So on each edge, you have an independent noise operator X that happens with probability P because of coupling to the environment, or all kinds of noise. Okay, so once this happens, while you have a density matrix, it's not a pure state anymore because it's coupled to the environment, and the density matrix is an incoherent or classical mixture of states with anyons, okay? Because it's the Pauli X in the toric code, although it would be good with picture, but just let's just accept this, that the X creates pairs of anyons. So if you apply X to the state, with some probability, you create pairs of anyons, and you can kind of move these anyons around by multiple applications of this noise operator. So you get a classical mixture of states, excited states, with some anyons. So what's error correction? Well, error correction is the following. So as these noise are kind of corrupting the state, we measure the stabilizers to extract the syndromes. We know where these M anyons are, and then we kind of just pair them up, annihilate these anyons to restore the restore the Topological state, the code state. Okay, so that's a decoding. So using some algorithm, you can do this. However, we also know from this paper back in 2001 that this can only be done when the error rate, the probability of the error, the noise, is low. Okay? In fact, decoding is in principle possible only when P is below a threshold PC. The PC is 0.1, no, it's 10%. Okay. So to kind of summarize this fact in a slightly more formal way, so for P below PC, there exists a recovery channel, a quasi-local recovery channel, to bring this big state back to the Tori code. Okay. Essentially, this decoding algorithm gives you such a recovery channel. Now, this has been known for a long time, but recently has sort of been realized that we can also look at this picture as a phase diagram, of many-body mixed states. That there's this kind of transition between states which are decodable and states which are not decodable. Okay? And the idea that these really belong to distinct phases. No, I'm not going to define what phases mean here. It needs some generalization of the notion to mixed states, but no, it's intuitively makes sense that these are actually belong to different phases, and that's why you cannot decode what happens here, because the state has entirely transformed into something very different. Okay. If the error rate is too large. And here I'm thinking about the state just as a density matrix you get by corrupting the Tori code with a particular error channel that parameterized by P. I'm not thinking about the dynamical process where I'm measuring the syndrome, then performing active error correction. I'm thinking about this just as a kind of phase diagram of the density matrix, mixed state. Yeah. Oh, so I didn't write down the error channel. Sorry, that's a problem, I think. So the error channel on one side is this. So it's 1 minus P times rho plus P x rho x E. And you can see that you can perform just a unitary, just conjugated by x to swap these two terms. So P smaller than half and P greater than half are unitary equivalent. We don't have to go beyond P equals 1/2. It's also intuitively clear because P equals 1/2 means that error occurs with equal probability. So that's the maximum we can imagine. Right? No, with or without error, it's equal probability. So that's why the phase diagram is only drawn up to P equals 1/2. Okay, so that kind of raises the question right now. How do we think about topological phases in mixed states? So I'm not going to talk about general mixed state. I'm just going to talk about a mixed state that everyone is familiar with, thermal state. No, what can be more familiar than the thermal state? It's a mixed state. And there's a kind of interesting question in confirmation theory about the thermal stability of topological codes. No, of course, everything's in the real world, everything's at finite temperature. Never have a real temperature, zero temperature state. So it's a very relevant question to think about what happens at finite temperature. Okay, so for 2D topological codes, the kind of polystabilized code that we talked about earlier, this question was answered by Matt Hastings in his paper, and here's my rephrasing of his statement: is that the finite temperature topological state is trivial in the following sense. Okay? So you can write the finite temperature density metric, just a Gibbs state, as essentially up to a quasi-local quantum channel, a short quantum channel, a short depth circuit, as a convex sum, a mixture of short-range entangled states. Okay, and then this is a kind of a trivial mixed state, so this state is trivial in this sense. There's no long-range entanglement anymore. There's only classical correlation. All right. This is true for any non-zero temperature. Right. Here, N means a quasi-local quantum channel. Okay. Also, I haven't defined it, but you can imagine what it means. I'll let you imagine what that means. Okay, so the definition is that it can be purified into a quasi-local unitary circuit. All right, but this is not, if you go to other dimensions, this is not generally true. So if you go to 4 dimensions, there's a particular code, the two-form toric code, that cannot be written as this form. And we will say it's actually non-trivial. It's really, and it is actually a quantum memory, self-correcting quantum memory at finite temperature. Okay, so that leaves 3 dimensions. And for other reasons, the self-correcting quantum memory, the question of self-correcting quantum memory is also kind of a complicated one in 3 dimensions, although it's not directly equivalent to this discussion. Okay. So I just want to give an example that we believe is a thermal state of a topological code in 3 dimensions that's actually non-trivial in the sense that I just discussed. It cannot be written as a convex sum up to a quasi-local channel as a convex sum of short-range entangled state. Okay, so you can imagine that it's not easy to look at this code. It's kind of a twisted version of toric code. Again, I think first written down by Michael, but although it has come up with in a number of different contexts. Okay, so it's a poly-qubit code, poly-stabilizer code of qubits. Okay, and product of x. But then the plaquette terms are somewhat funny. You have to put some number of x around the plaquette. Okay. Let's not worry too much. Not worry too much about the details. Now, what's the physics of this? Well, I'm using these words of higher form symmetry, but what's really happening is that this toric code is a 3-dimensional Z2 gauge theory. However, the gauge charge is a fermion. That's what it is. Okay. And this funny arrangement of x is to make the particle fermionic. So the string operator for particle, it's more or less just a product of z, but then you have to kind of put around it some number of x in order to commute with the plaquette terms, and this x makes it fermionic. So in the language of higher form symmetry, the 2-form symmetry is anomalous for this code. Okay. The 1-form symmetry is not anomalous. Okay, so before talking about the entanglement structure, let's look at what happens at fine temperature, just thermal phase transition. I decided to plot the topological entanglement entropy. You can calculate this for this code at finite temperature, and then you get the following. Okay, so a similar calculation was done for the untwisted version, the kind of a garden variety toric code in 3D by Castelnuovo and Chamang some time ago, and the calculation can be generalized to this more complicated twisted code. Okay. So what you get is following. So at 0 temperature, just a finite number, it's actually 2 log 2. If we go to any finite temperature, it drops to log 2, and then stays log 2 for some time until you reach some critical temperature. There's actually a thermal transition here, and then goes to 0. Okay. So at 0 temperature, it's a code, it's a stabilizer code, it's a quantum memory. You go to finite temperature, any finite temperature, that quantum memory is gone. It's just lost. But then this log 2 here means that you still have classical memory. Okay, not particularly useful as quantum computation, but okay, you still have classical memory, and then the transition is where the classical memory actually gets lost by thermal fluctuation. All right, so the interesting part is this regime. You mean this one? It is a thermodynamic phase transition. Actually belong to the 3D.
This entropy doesn't just go from 1 to 0 with the transition?
Yeah, I guess this is a plot in a finite size system, so it's no. It really should be a step function. Yes, right. In the thermodynamic limit, it's just a step function. Yeah.
So in the classical memory case, you don't have a long range.
Well, so what I'm going to claim is that here there is actually some sort of long-range entanglement, although it's not enough to give you a code, but there's some long-range entanglement, some subtle form of long-range entanglement. Well, to compare the untwisted version where you don't have these funny, red edges along the plaquette, that is actually just short-range entanglement here. Okay, so here's a precise statement. What one can prove is that for temperature below Okay, I write it using inverse temperature for temperature below some number, below Tc. So that's the best we can do. So below this temperature, for any short-ranging tangle state, sigma, I write the sigma, the trace distance or fidelity, whatever measure you like, to measure the distance between these two states, goes down polynomially as a function of system size. Okay. So it's very far from any short-ranging tangle state. Okay. So this is a statement. And here's a sketch of the argument. So what we do is, what happens is that thermal states has both particle and loop excitations. Okay, so that's the thermal state. They occur with some probability given by the Gibbs distribution. Now below this Tc, we can clean up, we remove all these loop excitations by a quasi-local quantum channel. Okay. But then without the loop, you restore the exact fermionic two-form symmetry, and that implies long-range entanglement. And that can be quantified precisely in this form. Oh yeah, I was using fidelity, and then somehow I decided to change it to trace distance, and then okay, let's say this is actually fidelity. Sorry, that was just plainly just wrong. That's wrong. Yeah, this should be fidelity. Yeah, fidelity is small. Okay, imagine this is fidelity. So for trace distance, it will be 1 minus this, greater than 1 minus this. Just to compare, the untwisted version where you don't have this funny X on the plaquette is actually short-range entanglement, shown explicitly in this paper. Okay, so, there's an interpretation of this statement in terms of how fast you thermalize the state, that you cannot have rapid mixing or rapid thermalization for this particular state if you start from a short-range entangled state. All right, so that's all I want to talk about. Here I just list a few other things that are relevant in this context, but obviously I don't have time to talk about them, including what happens in 3D topological codes. They're wild. They have given you all of these fractal topological order and defects and boundary, gates, etc. Okay, so I end here. I guess I'm taking too much time. Thank you for attention. I'm also going to nominate Arpit and Shuhen as the leader of discussions. So unfortunately, Arpit, the last name is too close to mine, so we are both in red group. So one of us has to go to another group. Yeah. I think Shuhen is probably a different color. So. Okay, good. All right. And have you got any questions?
You said rapid, that can't thermalize rapidly. You say slightly more quantitative.
Oh, yeah, rapid. So here's a precise statement. So you start from some initial state. Of course, to talk about time scale, we need some explicit dynamics. Let's say you choose what's called the Davis generators, the kind of a Markovian evolution you get from recoupling to a finite temperature bath. You can write that down. There's a particular kind of a Lindebladian evolution. Now we ask, how long does it take for the initial state to kind of reach the equilibrium? That can be measured by trace distance up to some error epsilon, let's say. So the question is whether the time scales as a polynomial of system size or as a log of the system size, a polylog of system size. If it scales as a polylog of system size, we say it's a rapid mixing or rapid thermalization. So example, we can show or prove actually that there was a proof, there's a proof in general. In 1D, thermalization of local commuting projectile Hamiltonian is always rapid mixing. And that kind of agrees with our intuition that in one dimension, finite temperature states are all trivial. Okay? And you can also prove at sufficient high temperature, you have rapid mixing in higher dimensions too. Okay? But low temperatures, always the kind of the hard part where the techniques are not applicable, except in 1D.
So as you're saying,
So I think rapid mixing means that it's a polylog.
The polylog, that's the statement here.
It happens within polylog time. So it's a fast thermalization. The time,
rapid thermalization.
Oh yeah, here is no rapid mixing.
Takes it
It
more
takes
than
at least
that.
polynomial time. It should take polynomial time to thermalize, at least more than log, any poly log. Yeah.
Imply that you would have a finite temperature stable quantum memory.
So unfortunately, this state is not a quantum memory.
Okay, so it's very far from any short-range entangled state, but still you cannot encode the qubit in it.
You cannot encode the qubit. So that's bad news, but it's still it's not short-range entangled. So to get a stable finite temperature memory, you need to go to 4 dimensions. That's a 4-dimensional toric code. The 2-form toric code is the stable quantum memory at finite temperature up to some critical temperature. I think there was a question.
So can you say it differently using quantities like coherent information, which imply that there is no recovery channel? Because you want to show that this is not self-correcting, but the topological order is thermally stable.
Well, so yeah, so I guess this is what we have. So what we can show that it's very far from any short-range entangled state. Okay, I think you mentioned some measure of entanglement. I'm not sure I follow that.
Well, if you calculate coherent information, there are phases for which coherent information can be
coherent information.
Yes.
Yeah. So I think coherent information measures whether you can encode a qubit or you can encode information in the ground in the state, and we know this state doesn't encode information. So yeah, coherent information doesn't tell you anything. It's just trivial. But still, this state is not short-range entanglement. It's a good question of whether anything else meaningful or observable we can say instead of just saying that it's very far from a short-range entangled state.
I think we've gone a little bit over time, so let's take a small